A catalyst is just a chemical that can make the speed of the reaction faster. And a catalyst is pretty cool because it's not used up itself. So if you put one molecule of a catalyst in, it can have lots and lots of transformations go through it before it's actually used up itself. So we rely on catalysts a lot. Our bodies use lots of catalysts to make a lot of the things happen for life. In biology, anything with an ASE ending is basically a type of a catalyst. But that's for biology, not for me, that's for sure. But anyway, catalysts can be really cool. So in the pictures there in the lower part there, you have an example of a catalyzed pathway and an uncatalyzed pathway. In the uncatalyzed pathway, reactants go to products. It's exothermic in this example, but it's a single step, and you can see how the energy of activation is pretty high. So what a catalyst does, which is in picture A, it lowers the energy of activation barrier down. So it's lower barriers is like a lower hill that you have to go over on a bicycle. It's easier to do. It'll be easier for reactants to go to products. Now, catalysts work by somehow injecting themselves into the chemicals and then re-emerging unscathed at the end. So what that means for us is that catalyzed pathways have to have at least two humps, at least two steps in the mechanism in order for reactants to go to products. Without the catalyst, it's easy to go reactants to products by itself. But with a catalyst, you'll have at least two steps in order to transform those reactants to products. So it provides an alternate reaction pathway. It's the same overall exothermic, endothermic kind of considerations, but you do have a lower energy of activation, which makes it faster.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface. A significant source of air pollution in many cities is the emission of nitrogen oxides by gasoline engines. The problem is not as severe as it was a few decades ago, due largely to the advent of devices called catalytic converters installed in automobile exhaust systems.
A catalytic converter is a great example of how a catalyst has helped our society a lot. And in the early 70s in Los Angeles, places like that, smog was a real problem. And it was mostly due to exhaust from cars. It would react with the water, it would make it very hazy and stuff. And it wasn't good to breathe, jazz like that too. Well, the introduction of a catalytic converter to a car allows some of those smog-creating chemicals like carbon monoxide and nitrogen monoxide to be created into other chemicals. So carbon monoxide is usually turned into carbon dioxide, while nitrogen monoxide is turned into nitrogen and oxygen. And those chemicals, at the very least, aren't as bad for humans. Carbon dioxide certainly is greenhouse gases, so I'm not saying we're totally scot-free, but at least it doesn't create the smog effect that we see, and it's healthier. Auto exhaust systems with catalytic converters often use an expensive transition metal. Platinum, palladium, sometimes nickel are used. Sometimes you hear about people ripping off catalytic converters from cars because the metals inside are worth a lot of money, unfortunately. However, the big picture, they make us all a lot healthier, and I personally don't think they should do that, but who am I? I don't know anything. Anyway. Other uses of catalysts include making all the plastics that we use. Polymers are essentially plastic. We'll talk more about that in Chem 223. You can take ethene, which is CH2, it's got a double bond, and turn it into polyethylene, which is used for lots and lots and lots of different kind of substances. Making acetic acid, vinegar, from methanol, CH3OH, is actually a good use of a catalyst. And again, like I said, all of our bodies use catalysts all the time. Enzymes are biological catalysts, and without them, we wouldn't be able to do a lot of things that we take for granted as human beings. This is a picture from 2025. It shows turning an alcohol into an aldehyde. Now, the alcohol would be like methanol there, CH3OH, and it's turning it into an aldehyde, which is a carbon hydrogen with a double bond on it. It's pretty cool. This is a brand new thing. It uses some kind of molybdenum catalyst. A lot of times the identity of the catalyst is kind of a trade secret. They don't usually reveal that, which is fine. I just think it's kind of cool that they are starting to get movies of this kind of transformation.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
We've talked about the decomposition of hydrogen peroxide into water and oxygen, and hydrogen peroxide will decompose eventually to water and oxygen. It's true. However, if you add a catalyst, as you can see, it goes a lot quicker. Manganese 4 oxide, i.e. manganese dioxide, is one example of a catalyst that makes this happen. But now that we understand the diagrams, we can create a picture like the one there in the lower right. So the black line represents the uncatalyzed reaction of hydrogen peroxide to water and oxygen. It has a higher energy of activation, so it will happen, but it's a bigger hill to overcome. And so it's harder for the reactants to get the right amount of energy to overcome it and become products. If you add MnO2, however, it catalyzes the reaction. So it lowers the energy of activation considerably. It's a lot easier for the hydrogen peroxide to break down. And like all catalysts, then, you have two humps. The first hump will be for how the MnO2 injects itself into this system, and the second hump there will be how the MnO2 somehow gets itself away from the system and is recreated at the end. So in the video, that kind of brown water there, if you'd evaporate off the water, you'd have MnO2 left over. You could reuse the MnO2, make it break down some more hydrogen peroxide. Catalysts are pretty exciting. This is a picture of taking a compound called cis-2-butene and turning it into trans-2-butene. The cis-C4H8 is being turned into trans-C4H8. Now, if you look at the overall reactants to products, products are a little bit lower. This is an exothermic reaction, so it will happen. But if you don't add a catalyst, that black line shows you much higher energy of activation. It's a much slower reaction having the cis go to the trans. If you add, though, iodine, I2, it tends to catalyze this reaction, and it makes it have a much lower energy of activation. So those red bumps up there show the different steps. In this case, the slow step is in the middle, and this is something you can figure out too. We're not going to talk about it, but the middle step is the slower one. The important part here is that if you want the cis to go to trans, add a catalyst. It makes the reaction a lot easier to happen. That barrier is lowered quite a bit. It's easier for the reactants to go to products, and you are good to go.